Yeah, now you can't hear me. No, you can hear. Okay. So it's my pleasure to introduce Zoë Coull from Ice Dragon. She's the CEO of Ice Dragon, and she has worked with the Correct program since the beginning.
Yes.
And we met each other because Joey Kish from McMaster was saying, you should talk to Zoe.
That's our origin story. It's not very exciting, but yeah. Yeah.
But Zoe has been in the program committee since the beginning. She has made a lot of decisions for this program, and she also has taken a number of interns.
We
And
have one
Maida is
with
currently
joining us today. Yeah. I think you're the fourth one to come through as an intern for Ice Dragon. Yeah.
yeah,
Very cool.
yeah. So you will hear more from Zoe about her.
Yeah. Actually, maybe the fifth. Actually, yeah, we still are still working with Kiana from last year.
Ah, yeah.
And we're hoping to hire Nicole, who was the first one. So she's hopefully starting with us in September. So we've had a lot of very, very good students through the program. So it's been awesome. All right. So we are going to talk about corrosion risk management today. So if you look at your curriculum, you might want to throw it out because I've made some changes. But first, I'll give you a little introduction to myself. So I've spent the last, sorry, Phil, 30 years. I know it's a long time. 30 years in materials and corrosion. I started off with an undergraduate in materials engineering from Imperial in the UK. I then went on to do a master's in corrosion, specifically at UMIST, now Manchester University. I then actually worked for about 3 years in a big consulting company in the UK, mostly looking at highway infrastructure and the rehabilitation of different reinforced concrete things for about 3 years. And then I came back to school, and that's how I ended up in Canada. I came to do my PhD with Roger Newman at the University of Toronto. Since then, I did have a little bit more of a foray in the sort of large engineering consultancy company before thinking, no, thank you, and starting my own company about 10 years ago. So I've been the CEO of Ice Dragon Corrosion. I haven't actually really been calling myself that until the last few years because it didn't really fit right, but I'm sort of growing into that now. And so, yeah, I've had this amazing career in materials and corrosion. So I'm really pleased to see so many of you in here getting interested in this area because it really has given me so many avenues to learn, so many opportunities. I've also popped at the bottom of the slide here what I value. So we're going to come back to this afternoon because we're going to have a bit of time at the end of the day to talk about what you value, what your personal values are. You're already ahead because we already did this exercise together. But so what I value, integrity. So what does that mean to me? So that means that you're going to turn up, you're going to do what you say you're going to do, and you're always going to do the right thing regardless of the cost to you. Growth. Always be interested, always be looking to learn something new, looking to learn from other people, making sure you ask the right questions as well. And then compassion. So the reason that compassion is on my list is because I didn't find this in my working life outside of Ice Dragon. So having compassion means taking care of yourself as a first step. You can't show up for anyone else if you're not good, but then taking care of others, being kind, listening to people, practicing empathy, and also practicing rest, which is actually, I would argue, a very core leadership skill, right? Resetting yourself, making sure you've got the resiliency to show up. So we'll get into some of your values this afternoon, but I just wanted to sort of share those with you because they're the guiding compass of how I've driven my career. All right. So I think what we're going to do today, and hopefully we're going to get through all of this because there's actually quite a lot that I've tried to pack in. But this morning I want to go through, it's more of a technical start to the day. I want to sort of go through how to use a corrosion risk assessment. So I don't know if folk have come across this before in other areas, but we're going to do that this morning because it's a very, very useful tool for a corrosion engineer. We're then going to start getting into introducing you to the standard framework around how do you build a corrosion risk management program. We're then going to eat lunch, apparently. I don't know if that's here. I'm not quite sure, but it's here. Then I'm going to give you a bit of an overview of the corrosion risk management program that Ice Dragon have been developing for the Canadian Navy, so that you've got a real life case study to kind of put some of the learnings from the morning into context. We're then going to start talking about human factors and how those play into the creation of proper corrosion risk management. And then at the end of the day, we've got some time set aside for you guys to do some exploration on who you are and what your leadership styles are. So we're a little bit it does follow a flow, but I'm just trying to pick out we haven't got an awful lot of time to go through everything today, but hopefully we'll be able to get through all of that. So I was having a little think about, I was actually just invited to write a chapter for ULIG's corrosion handbook on corrosion risk management. And so I started to think, okay, well, where did we even come from? Where did this discipline of corrosion engineering come from? Well, it was actually in the sort of 40s and 50s that this started to emerge as its own discipline. And then sort of around that time, NACE International was founded, which you'll all know now as AMP. And it was really created to start putting standards and training around this new discipline that was emerging. So really it sort of came to the forefront, corrosion came to the forefront because of really the Industrial Revolution and all of the heavy industry that started up. In the 90s, we started to see a major shift in the mindset away from just sort of fixing the technical problems to more of a risk-based approach, right? So we had some standards that came out around that time that we started to use that were really helping us to use the technical data to make better decisions. In the 2000s, we had some pretty high-profile industrial disasters. I'm old enough to remember the Piper Alpha disaster in the 80s. So there were a lot of these big catastrophic industrial events that happened where corrosion and asset integrity were playing a causal role in why these things failed. And so industries and regulators started to create more structured frameworks about how we were managing corrosion risk. And then we also around that time started to see more standards and frameworks available around asset management generally. So when I talk about asset management with my mother, who's a financial person, she's like, oh, I do that. And I'm like, no, it's completely different. We're talking about asset management of physical assets. So what are the sort of best practices and frameworks and processes and things that need to be in place in order to manage these? In 2016, was actually quite pivotal, certainly for me personally, because that's when I started my company. And it just so happened that fortunately, that was when the NACE impact study came out, right? So they actually went out and they formally pulled out all of the best practices around corrosion risk management from about 243 companies across all different kinds of sectors globally. And really what they were trying to do is say, okay, for the companies that are managing corrosion risk, what are they doing well? What are they not doing? What is it that creates a really good framework from all the learning that we've had? And actually in 2019, they took all of those learnings and those best practices and they created a framework for creating corrosion risk management programs. We're using that framework at Ice Dragon. Other organizations are as well. And we're going to go through that because I think it's really important today that you kind of walk away with some tools and knowledge of how do we actually create these programs. And then the final bullet there is something that I'm sort of working on. This is kind of where a lot of my thinking is going right now. We have good technical solutions that have been created really since the discipline started. We've got risk-based approaches. We now have this framework to tell us what needs to go into a program. But the missing piece for me that we've discovered at Ice Dragon is we haven't really embedded the human factor piece into this framework as strongly as we should be doing, right? So we're talking about, if you have the right technical solution, that's great. right? You need processes in place to manage it. That's also great. But you actually need people to do the work, right? So if you aren't considering how people in your program, people in your project are actually impacting the effectiveness of your solution, you're missing out on an opportunity. So we'll go into more about that later, but it was really just to sort of give you a little rundown of how we got here. So why do we care about corrosion? So we're going to go around the room and ask everybody, why do you care about corrosion? Why are you here? What is it about this subject that interests you? So in fairness, I'll give you a few minutes to think about that because I know it's still early. So for me, my why I am here story started when I was 17 and I was sitting in an undergraduate class, probably at the back of the class knowing me. And we had someone come in from Lloyd's Register. And he was telling us about this big oil tanker that had failed. There was oil in the sea. There was these safety issues, and it was corrosion fatigue. And I was suddenly like, oh, light bulb moment. So at that point, I was actually an active member of Greenpeace, and I was like trying to save the world and the environment, and it was very important to me. But I was struggling to find out, okay, where can my impact be, right? Because I also had this love of science, this love of engineering, and I was like, oh, corrosion is it. If I can fix corrosion, then I can stop all these assets from collapsing, and I will help with, you know, safety and the environment, and it's going to be awesome. So that was kind of my, you know, obviously quite juvenile reasoning at that age. So why are you here? Phil, go ahead. I can pick on Phil. I can pick on Phil. Yeah.
Why am I here? So I didn't care about corrosion until I had to learn it in my master's, and I was like, this is interesting.
Yeah.
And I don't really like chemistry. But somehow it keeps coming back. Like people ask questions about it, and it's an interesting problem. Like from like if we're thinking about the range of things that we're gonna do this week, we're doing like art corrosion, and then also like the water does not work in Calgary because we had a corroded pipe. So
right.
like and then seeing those pictures of the nasty sludge.
Oh, that was yesterday.
A little bit.
Yeah. Yeah.
Yeah.
Yeah. Only wine. Yeah. Oh, yeah. Yeah. Good. Okay, so Yolanda, why does corrosion draw you in?
I like to see the risks and things, and corrosion is perfect for that. And I like to have lots of disciplines, and corrosion is perfect for that too.
Yeah. We're like friends with everybody. We often work with everybody. Yeah. Cool. All right, let's go around the table. I'm gonna pick on my lovely intern over here. Mady, go ahead.
So coming from an environmentally friendly background of biology, whenever I saw a spill in the environment, because my master thesis was about bioremediation of oil spills.
Yeah.
So that one was exactly like yours. What's the root cause of that?
Yeah.
So that was the point that I was like, okay, that's something that microorganism may play a role in it. And it was like a aha moment, and I wanted to study corrosion more and more.
Excellent. All right, go around the table. Yeah.
So sorry, something that I realized is that corrosion, of course, costs a lot for the governments, for the companies, and for everything. So something that I care is that if we can prevent some of these things, they can actually save lots of money, and then that money can be spent on so many other things, like beneficial things.
Yeah.
But right now it is kind of a big waste of money every year by companies, by the government.
Yeah.
So that's something that motivated me.
Excellent.
Yeah. About corrosion, I can say that corrosion can happen everywhere, even inside of the body. Currently, I'm working about the corrosion inside of the body for those implants that people, especially those who had some surgeries or had some accidents and need to change their joints, or they became old, they need to change those things. So if they have those corrosions inside of those body, so they should experience more bothering to have the second surgery to replace them.
Goodness, yeah.
Something like metal release inside of their body. So we should think about the corrosion of those things inside of the body, as well as those things that we have outside in the industry or everyday use. So
cool.
it could
It's a cool area. Go ahead.
Something worse.
Thank you.
For me, nuclear kind of focus, and
Yeah.
obviously physics can tell you a lot about how a nuclear reactor is going to perform theoretically, but then corrosion is always kind of the buzzkill in terms of how long you can actually operate that nuclear reactor. So it's fun to be in that particular space because you're kind of grounded.
Yeah.
Everybody out here is shouting all these fabulous ideas, but then you have to do the study and actually say, no, this is actually.
Yeah. Yeah. Buzzkill, I think, is a good description for what we do. Yeah. Good. Go ahead.
Buzzkill, especially for me, because again, it's clear, but I'm working on reactors that don't even exist yet. Probably won't either.
Yeah. Okay. Yeah.
The main thing for me with corrosion is more of the diversity that you get. Like someone had mentioned before, you get a lot of different disciplines and you get to learn a lot more things you otherwise wouldn't have. Like yesterday, we learned a lot about biology, we learned a lot about physics and other things.
Yeah.
It's just very fun.
Excellent.
I'm coming from chemical engineering background, and I found that corrosion in a plant can lead to risk.
Yeah.
That impact to safety, environment, and cost a lot.
Yeah.
And
For me, I think the corrosion will result in the safety problems because when I'm at the master, I focus on the spontaneous combustion of hydrogen because of the pipeline will leaks the hydrogen and will result in the self-ignition. So I think the corrosion is a major problem for this issue.
Yeah.
Yeah. So safety is very important.
Excellent. Good. The same. Yeah, you're working on a similar project.
It can affect our safety and loss of money. So, but it's everywhere. So I think it's very to prevention of corrosion.
Yeah, I agree. Thank you. Go ahead.
So I have a background in chemical engineering.
Yeah.
So in my undergrad and when I was working, I feel like corrosion is a field that people ignore until it becomes the problem. So when I was working back home, there was a material failure and we had to shut down the whole facility for like 2 weeks. So us as chemical engineers, we're like, okay, so this is a thing. And
yeah.
like no one really pays attention when it comes to the degradation of equipment until it becomes a problem.
Yeah.
So that kind of was an eye-opening to me. It's kind of a field that might be interesting. So yeah, so I'm working towards.
What industry were you working in?
So it was a municipality. So
okay.
The treatment.
Okay.
So I think they hadn't been maintaining this underground pipelines for years.
I can almost guarantee they weren't. Yeah.
Because we honestly thought that maybe the inspection team, they used to just come and look at the general pipes, the visible ones, and no one ever checked the underground pipes until it became a problem.
That's very good. Oh, and last but not least.
Honestly, for me, it was just because it's a complicated problem.
Good.
It has so many different physical processes happening at the same time that I'm doing modernization. So I was just curious of how hard can it get, and I don't like doing simple stuff. So I said, why not? And plus, the fact I'm coming from a physics background, so everyone.
Okay.
Like physics,
yeah.
star, And I just like the fact that my research is a tiny bit useful compared to the people doing physics.
That's excellent. Good. Good. Yeah, go ahead online. Two online.
Cares about corrosion because of human, environmental, and cost impacts. The other I haven't read.
Oh, you're from the Maritimes. So lots of high industrial activity. Oh, environmental pollution and impacted Indigenous communities. Yep. Excellent. Thanks, online people. Good. So I probably don't need to go through the next few slides that I've got because they're following on from the theme that we've heard already in the room. I think to your point, we know why corrosion is important, but when you ask someone that's not a corrosion person why it's important, they don't get it. They don't understand until it's too late, right? But corrosion kills. I know that's a bit of a dramatic headline, but it does. There are many case studies where you can dig in and you can find that corrosion played a causal role in a catastrophic collapse or an industrial incident. This is just an example of one where we had a bridge in Italy that collapsed and 43 people were killed, and it was because no one was looking for the corrosion in the right way. We had a mall collapse, I think, in Ontario, probably about 10 years ago for the same reason, right? It's not just reinforced concrete, it's all kinds of materials that can fail. About 6 years ago, I was about to do an inspection in Chile for a client of a ship loader. And then about 50 kilometers south that morning, a ship loader collapsed and the operator was killed because of corrosion of the cables, right? So it doesn't matter what industry you're in or what kind of asset it is. This is pretty broad, right? So we know that there's a direct link between corrosion and safety, as so many of you have already pointed out this morning. We also know it costs a lot of money. This was also something that was raised as well. And I really like the perspective that you brought, where you're like, if we can save money from doing it properly, we can put that money elsewhere, right? So from a company perspective or an organization perspective, from a government perspective, that's very helpful, actually, right? Maybe we could be putting it into healthcare or something. Go ahead.
Yeah, there's a cost to it, but it's also depreciating all the assets that you...
It does. Yeah, exactly. Yeah, and I think as well, like we can get a pretty good handle on what the direct costs are, and in fact, if you look in the impact study, it will sort of talk about that. But there are also indirect costs associated with corrosion as well, which we found very difficult to measure, that are often at least an order of magnitude. The same order of magnitude as direct costs. So this means it's, direct costs are things like your materials or your replacement costs or something like that. The indirect costs are more, have you got environmental fines? Have you lost production? You just told us about an incident that shut everything down for 2 weeks, right? In mining, if you have a shutdown for 2 weeks, someone's getting fired somewhere. That's all I know, right? So that's important. And then, of course, we've heard a lot of this as well across the group. We know corrosion pollutes. We've got pitting corrosion as a leading cause of pipeline leaks. So many examples of this, right? We recently had a client, a gold mine. They were using cyanide in their process, and there was a leak in the cyanide circuit, right? So we had, immediately there's a remediation, there's a lot of stuff that has to happen. They did a very good job of it, but it shouldn't have happened in the first place, right? So I think we sort of all have a good understanding of like why corrosion is important, but you're all in this course, you're all studying away, and you're really focusing. Well, I found I really focused when I was in school on the technical solutions. What are the right technical solutions? But it isn't enough to show up to solve the problem of corrosion with good technical solutions, right? We need to actually create corrosion risk management systems. So the system is a combination of the very good technical solutions that so many of you are working on, plus processes, plus people. So we're going to spend the rest of the day kind of looking at some of these. And but just to sort of drive it home a little bit, it's just a sort of made up example, but it was really just to sort of show, imagine that you're on a project, right? Your client is in Indonesia. It's a big mine site in Indonesia. I have one in mind, but I won't say names, right? They're having rapid deterioration of their coating on structural steel. You're going to come in and you're like, I have a great solution. I'm going to give you this specification for this amazing coating that will do all of these amazing things. It's going to be great, right? But the site team doesn't really have the skill set required for implementation of this specialized system. They don't really have a robust quality assurance, quality control process. What would happen if we only focus on just giving them the right solution? If that's the question. Go ahead.
Of what you're proposing, right? Yeah. Because they can't
do it, right? And so sometimes we have to always pay attention to what is the situation that we are putting this solution into, right? Do they have the processes? Do they have the training? Do they have the budget? Do they have, so all these different things are working together to make sure that we get the technical solution. If we just went in at the moment, and this is an actual client that we have right now, I know if we just go in and say, actually, you should be using this coating, get it done. This is kind of what we would end up getting back. It would be comments around, oh, you over-engineered this. We can't even source this. There's something wrong with the system because we put it on and now it's falling off. It's the vendor problem. It's the manufacturer problem. We didn't get any value out of this. And then often you get people just sort of giving up, right? So we've kind of missed really important input from a design perspective from the process and the people side of things. We might have the best solution, technically speaking, but if we can't implement it and get it to work because we've missed out this other information, there's no point doing it. We'd be better going with a bog standard epoxy and calling it a day, right? So we have to think about process and we have to think about people. So we're going to kind of walk through this a little bit today. I'm not going to go into the corrosion engineering and the technical piece because you guys are already doing that. But we're going to start with how do we use those data in the best way to start making decisions. So we're going to look at corrosion risk assessment. Then we're going to get into, well, what are the processes and what's the structure and the framework that we should be using in order to create a corrosion risk management program. And then we're going to get into the human factors aspects. I'm not a change management expert. I haven't done any training in change management. We've been working with professionals in this area for years. So I'm just going to share with you what I know. I just want you to understand I don't know everything. And if it's something that interests you, like I know, sorry. But if it's something that interests you, like this is an area where I'm really focusing my kind of learning right now. So if it's something that does kind of spark your interest, I have loads and loads of references for you as well. So corrosion risk assessment, does anyone in the room have experience of using a risk assessment approach? Yeah?
I read your book that you told me to read.
You read the book?
The expensive one, it was like $300.
Yeah. That's excellent. So Phil's good. And you've had some experience as well? Okay.
And we'd have a lot of things rusting all over.
Okay, good. So this table's going to have a little head start maybe on other people. Anyone else? Mayday, you've used it as well. You've used it with us. That's what she's already ahead. That's good. Okay. So a risk assessment, really it's just another tool for you to help you with decision making, right? It's a very structured approach to looking at all of the risks. Yolanda will like this. You make risk registers. You really think about what are the defects that could occur and how you're going to control them, and giving and assigning a sort of numerical value to those risks so that you can prioritize and go through them in a systematic manner. So we use this as well to sort of answer the question of what is the most important thing that we could be doing here with the resources that we have, whether those resources are people or budget is obviously a big one. But we need to be able to justify as corrosion engineers why we're recommending we do what we are recommending, right? So you could do everything, right? But we can't do that. It's not practical. So we have to sort of focus ourselves and our resources, and this is a tool that helps us to do that. So for those of you who've used these before, this is going to be very simple. We're just going to go through it at a very high level today. But risk is really just probability multiplied by consequence, right? So the likelihood of this defect occurring and what could happen, what's the impact of this if it fails in this way. So very, very simple. And normally you'll see risk matrices that look like this. So you're assessing for what's the likelihood, not very likely, probably might not happen in the next 20 years. So we're going to assign it a level 1, right? But if it does happen, maybe the consequence is high, right? If this does happen, maybe the bridge collapses, right? So we're trying to figure out how to prioritize all of the different defects for a specific asset in a very structured way. So we've got a little example here. So we're gonna, I just bought a new car. So I was thinking about how about using an example around the probability or the risk associated with driving on the highway in the rain, right? So the probability is what's the rate of a probability of an accident happening on a scale of, say, 1 to 5, 1 being highly unlikely, 5 being almost certain. If it's me driving, probably not 1, slightly higher than 1. But let's say 3, there's a moderate chance of this occurring, right? The consequence is, so then you look at the consequence and you have to give the consequence a rating or the impact of that thing occurring, right? So then you're looking at, okay, it's going to be a minor inconvenience, probably not if you're driving at speed, right, on a busy highway, or 5 being a catastrophic event. So let's say we choose 4. So it's very, very simple. So then you end up with the risk calculation being 3 times 4, which everyone could do. We're at a risk level of 12, which if you look at our matrix, we're sitting over here, right? So often there needs to be a decision point when you're doing these risk assessments around what is the risk level that you can tolerate, right? In this case, we're talking about what's the risk that I can tolerate as the driver of that car, right? Am I going to bother doing anything with this risk because it's here? Or is it only when it gets into this kind of red zone that I'm going to start really worrying about it, right? Organizations have formal risk sort of approaches that they use, and they will have their own tolerances, right? So say this was a bridge. Let's go back to our bridge example. We may have a client that says, okay, our risk tolerance is anything that's in the high zone must be addressed. This is a non-negotiable. We're also going to add in anything in the medium risk sector that's 12 and above, right? So you're starting to narrow down where your focus needs to be. So you've got all of these defects in your bridge. You know which ones are, you've assessed them all, and now you know which ones you're going to focus on because they're either high or medium high. And those are the ones that are going to get resourced because those are the most important ones that we need to do something about, right? And then maybe you're saying, okay, the ones that are 12 or 9 to 11, those are the risks that we are going to monitor more closely because they're kind of a little bit on the cusp of our tolerance level. And then the low ones, we're just going to routinely monitor. So you're starting to use your assessment to actually drive very targeted, focused actions. And that's really the sort of the usefulness of this tool. So the other nice thing about it, and Yolanda's going to be like, yes, is it forces you to actually sit down and think about what are all the possible things that could go hideously wrong here, right? What are the risks? What are the defects that could occur, right? So if we go back to our bridge again, you are going to go through that bridge at a component level, right? So you might look at the deck, you might look at the abutment, whatever it is that your components are, the major components in that bridge, and you're going to say, what are all the things that could possibly go wrong, right? So you're thinking about, okay, de-icing salt attack and spalling and things falling off and cracking and loss of rebar section and you know, all pothole. Like you're going to go through the entire list for every component in that asset, and you're going to assign each item a risk value, because then you can go, okay, we've done it for the whole bridge. We only have $2 million. Right. Well, we're going to go and we're going to figure out those high risk actions and start to lower the risk profile of that asset. Right. So if we go back to our driving in the rain example, actually, maybe we won't do that right now. We'll do that in a minute. So the first thing is that it forces us to go through and really do an assessment on what are the risks that we're seeing here as corrosion engineers. Sometimes you're going to have to bring in our friends from other disciplines, which is where we get to make lots of friends. But in this case, we would be bringing in a structural engineer, right, to look at our bridge. They're going to input structural risks that they're seeing, right? So it's a multidisciplinary approach. Then we're going to go at, okay, looking at, okay, which are the ones that we're going to control? And then you put the control in place and you do the risk assessment again. With this control in place, what is our risk now? Have we lowered it sufficiently so it now sits below our tolerance limit, right? And then we can also look at, if we do this versus this, what's the difference in the reduction of risk? So if you're thinking about me driving in the car, first of all, should we be worried? Probably. Are we driving in the rain? So we ended up with a moderate high risk for that activity. So we're going to look at that. I've decided that that's above my risk tolerance. What are the things that I can control that will reduce the risk of the probability of that event happening, right? So obviously, I'm going to drive at the speed limit. I'm going to have my headlights on. So I drive an orange car now too, so everyone can see me. So good visibility. I'm going to increase the distance between me and the car in front, right? Or I might even consider taking alternative route. So there are things that you can do to bring that risk level down to a more acceptable level. And then I can make a decision. Am I going to take the car out today, right? Probably not. No. Okay. No, I probably would, right? But I'm still going to drive now because the risk is tolerable to me. I've reduced it by putting some controls in place. Just a very simple example. What's that?
Christmas lights all around the car.
I'll put Christmas lights. Yeah, exactly. So we've been through like obviously very, very simple example of the car driving, but in reality, these matrices, normally what happens is a corporation and organization will develop what risk means to them, and they'll create their own probability matrices. So these are just some examples, right? So I can't exactly remember where I pulled these from, but some people will look at, you know, likelihood 1, 2, 3, 4, 5, right? So you're saying, oh, the likelihood of this happening is rare to almost certain. The language changes, but the structure is usually very similar, right? Or here's another one. It's going to happen at a frequency of less than 1 in 1,000 years. Seems quite low, right? So they've said improbable. And then all the way down here to frequently, something that might occur 1 time a year. So the sort of probability matrix has to actually make sense from the perspective of what's happening at the asset level, right? Like if we're looking at assessing corrosion, right? This doesn't really make probably a lot of sense, right? So we have to be a little bit careful that the matrices that we're using actually make sense and they're at a granularity that's going to be useful for us. Yeah.
Sector, because I can think.
Yeah. Yeah, exactly. Yeah, exactly. So if you have you may have your stress corrosion crack growing at like very small levels over 50 years. You still don't want that crack, right? That's still a massive risk for nuclear, but a crack like that in another piece of process equipment in mining, or for example, in a replaceable pump, you don't care, right? So this is what I mean. You have to be a little bit careful with the way that you assign probability. It has to make sense for what the context is. But there are loads of these, and you can kind of look at them and you can do some searching and you'll find lots, right? Consequence matrices, same warning. The sort of level of consequence has to match what we're doing in the context. They typically will look at health and safety, environment, and operation. And operation typically tends to link into finances in some way. So normally the organization, any organization, will have its standard consequence matrix. Often they have it for sort of a corporate level, and you have to bring it down and you have to say, actually, this doesn't make sense. Again, for corrosion, you have to adjust it to the levels that we need. Here we can see we're going the other way now. So down here, there's no health and safety consequence of this action happening. So we're going to assign it a 1. However, we've got a 5, which is a catastrophic event leading to the loss of a life or more, right? So you're sort of having to assess things on this scale. Here's another one here. This is here they've called it personnel, but actually it's really safe, health and safety again. Similar kind of scale here. So you're going to have these matrices usually come from the organization. Normally, when we go and we say, hey, we need your risk matrices, I'd say 95% of the companies will have something already that they're using at the corporate level. As corrosion engineers, we then take those and ask the question, does this make sense? Are these levels correct for the context that we need to use? And if they're not, we have to make some adjustments, right? But it's at least a starting point. So when we think about doing a corrosion risk assessment, yes, we're obviously, we've just jumped in and we've started talking about assigning probability and consequence rating, but there's actually a process that's involved with the whole, that sort of gives you the whole stream of how we approach it when we get into doing these for an asset. First of all, we're selecting what is going into this risk assessment. Not everything needs to go into a risk assessment. Not everything is really that important, right? Do we need to look at this tiny valve on that pipe that doesn't matter? No, it's not really a good use of our time. However, you know, do we want to look at the deck of this bridge? Yeah, probably, right? We've decided it's critical. And there are ways to formally do that criticality assessment. So normally companies will also do this. They'll do the criticality assessment, which components, which assets are critical for the operational health of the organization. And those are the ones that end up in this stream that require a risk assessment. We're then going to collect design and condition data. So we're looking at what is the material? Did they include a corrosion allowance? What's the coating system? What are the process operational requirements, temperature, pressure, flow rates? And often we're jumping into an existing asset. So what's the current condition of this asset? Do we know that? Have we got enough inspection data, monitoring data? So here we call this blueprint data, but it's really you're collecting all of that information in the background that you need to assess what defects are going to be there and how severe they are and what the probability is and how we're going to control them. Are the controls in place working? All of that information comes in here before we even start. Then we're going to assemble the right people in the team, right? So for our bridge, that's going to include corrosion engineers, but also structural engineers. If you're looking at a piece of process equipment, you might want to bring in mechanical engineers, chemical engineers. So you're putting your team together because you can do these just as corrosion engineers, and we have done them in the past, but then you're only seeing a small part of the bigger picture. You need to sort of ideally bring in that expertise to really understand what's going on. Then you're identifying failure modes. So what could possibly go wrong in each of these components in this critical asset of ours? Is it pitting corrosion? Is it MIC? Is it stress corrosion cracking? Is it general corrosion? What is it that we're actually assessing for? Then you're going through this process of assigning, well, how likely is that defect going to happen? And what happens if this defect occurs? Then you're doing your calculation to figure out what that numerical value is and where your risk values sit in your matrix. Like, what should we be focusing on, really, is the question you're asking yourself there. And then you're going to assess the suitability of the different controls. So say you have your structural steel, you've gone all the way through, you've ended up here, you're like, okay, structural steel on this bridge, and you always assess for no control first, and then you add the controls in and you redo the assessment. So you can say, okay, what happens if we now coat it with, I don't know, this epoxy versus a marine grade coating, right? Are we actually pulling that risk down into an acceptable level? And then finally, the piece that everybody misses, and I think you touched on this before, right? You've got to make sure that you don't just put these controls in place and then forget about it. Because a risk that you can't see, that you're not measuring, you've not controlled that risk, right? So you've got to then think about what are the pieces that we need to put in place long term for this asset to allow us to monitor the risk. And that could be, taking potential readings of your buried pipeline, or it could be an inline corrosion monitoring probe, or it could be visual inspection, but it has to be appropriate to the defects that you've got in your that you've identified, right? So what we're going to do now, I'm going to stop speaking because that was lots of words. We're going to actually get you guys to sort of work through this a little bit with me. So you are a corrosion engineer. You are the corrosion engineer at this site. Where do you start? You've been told to do a corrosion risk assessment. Someone in leadership decided it was a good idea. Where do you start?
I like those rusty things down there.
Yeah. What's the first thing that you do? What's the first question that you're going to ask?
If there's any failure, sorry about that. If there has been any failure or leakages.
That can actually be a really good place to start because it tells you what's urgent, what you really need to look at and get on top of.
Figure out like what they're actually handling in operations and yeah.
There's a step for that too. Where do you start? Right? That's also another piece, right? But if you're looking at this, you can see immediately that there's a gargantuan amount of things in that picture, right? You have to go to your criticality analysis. All right. What are we actually including in this risk assessment? All of it? Probably not, right? You probably want to pull in, I'm standing too close to it now, but we've got some, I think these might be CIL tanks over here. They're very important. We've got thickener maybe over here. We're going to go in and we're going to just figure out, okay, from a business operation perspective, what are the most important assets that we need to keep operating? Right? That's going to be the first question because that tells you, okay, like these are the things that are on the list. These are the things that we're going to focus on. Plus, really good point. Have you got any headaches? Are there things that you're already a bit concerned about? They might go in as well, right? So you have to kind of get yourself a bit organized. So the way that we usually do this, like I said, is criticality through a criticality analysis. You're ranking really what it's a very sort of high level assessment on what bits of your plant are really important from a business perspective. If this shuts down, we have no redundancy, operations stop for 2 weeks, right? Then you're gonna say, okay, this is a critical asset. This needs to be included, right? And again, usually these assessments, they are very high level, but they do look at all of those consequences that we were already looking at before. But this is really more of a screening tool, right? So then we've got, okay, we've said, I know we've got a process tank with an agitator, say, for example. What are the components that we need to include in the risk assessment? Because the components in that asset might have quite different defects associated with them, and the consequences of the failure of those different components might be different. So actually, you're like, okay, we want this tank in our risk assessment, but what are the pieces that are made up? Like what are the components within that we need to look at? And again, you do that kind of assessment of, right, we're including this, we're not including that. And then we have to collect information. So this is like our kind of collecting blueprint information. Not only are you collecting information on your materials of construction, specifications, design, all of that stuff. Your most recent condition data is very helpful, but you're going to start asking questions around, from a corrosion perspective, what are the factors that are influencing corrosion, so that we can figure out what our defects are, right? And it always goes beyond material selection. I always like to throw this up because we often forget, like when we're asking these questions, there are all these things that can impact corrosion, right? So obviously your material selection, but then you've got obviously your environment. Environment is important. If you're working on a design project, something that hasn't been built yet, it's important to consider not just the sort of normal operating conditions that asset is seeing, but also thinking about, okay, what are the outliers? What things could fluctuate, right? So we do a lot of work with mining clients, and the sort of the process exposure conditions can vary quite a lot, right? Particularly in the chemical sense, because the ore concentration and the ore chemistry changes just with digging in a different bit of the ground, right? So you have to think about that. What are the normal operating conditions, and what are those outliers going to look like? But it's not that your components may not just be seeing service, right? They may be seeing transportation. They may be quite often thrown in a field during construction for a year and just left there in the rain, right? So you have to actually think about, okay, what's the sort of full range of service conditions that I need to look at? Go ahead.
I find it's a big issue now, and that's probably like a huge thing for all of us. But a lot of operations or companies are trying to extend the life of assets beyond their actual design life.
Yeah.
Example of that right now, because
yeah,
stay on. But we only design it within a certain window, and then we're constantly trying to do assessment.
Push it.
And then maybe we're doing more monitoring, and we're throwing all this money on the
exactly really intended for that. And we'll go into so this afternoon we're going to go through the Navy example, which is exactly that, this like idea of life extension. In mining, we often find this as a problem too, because they're like, design for 15 years. That's all the ore that we've managed to locate. So we're just going to design for 15 years. And then they're like, oh, look, we found more. And you're like, okay, so now 35 years. And so it's the same sort of problem. Yeah. So that can sort of come into this assessment as well, as the service life, right? We did a project recently with BHP for the Jansen mine. So it's the new potash mine that they're building out in Saskatchewan. And they're like, we need this to last for 70 years, right? In mining, no one's ever heard of that, right? But in potash, that's the life of mine, because it just is. But you're also thinking about, okay, what temperature do I have? Molten deposits, molten salts, yeah. Condensation dew points. You're thinking about stress, compatibility. In this room, I'm sure no one was going to design something with a galvanic couple, but like it happens all the time. Do I have movement? Do I have entrained solids? Do I have abrasion corrosion type of mechanisms occurring? What's the shape, the design of this piece? Is that introducing stresses or dead legs, or what's going on here? So collecting the information is just like such a core part of what we do. Like if you don't have a broad view on the collecting of the information, you're going to come up with the wrong answers. And then we've been through this. Who else do you need in the room? This is where we make friends. That Janssen project I was just describing, we actually de-risked it from a corrosion perspective across every single component and asset that they had. So we were working with the structural engineers on the concrete and steel, mechanical engineers, the process engineers, like all of them, even down to architecture, the architectural group. So this is one of the nicest things about corrosion, because we connect everybody else and we make friends. So other disciplines here. Oh, and then the other thing here is if you've got an asset that's already in operation, super useful to pull in your operators, because they will have the operational background. They will know what's going on. If they're, you can bring in your maintenance teams, your reliability teams from site. They will give you invaluable information, not just what you're seeing in the inspection reports, but how it's operating on a day-to-day basis. Yeah, go ahead.
Operations are also fun because sometimes they'll just like do things that keep it working.
Yeah.
They're like just hitting it with a wrench or something.
Yeah. Yeah. It's not documented. They don't follow management of change processes for engineering changes and things like that. So that can be very, very important. We often also bring in vendors. So if it's a specialized piece of equipment, we did this recently for a filter press for a gold mine as well. We were like, we don't know how a filter press really works. So we pulled in the vendors and had them give us the information around what is normal operation. What are the defects that you see come up with your own equipment? So you're pulling in information, not just from the documentation, but also from different skill sets. So it's starting to look more fun now, right? You're starting to realize that it's not just this multiplied by this. You're starting to sort of see how these projects kind of evolve. Then you're going to identify your corrosion failure modes. So in your risk assessment, and I'll show you an example of one in a bit, but you've got to have one line item, one assessment done for each type of defect. So if you think, oh, for this component, there's going to be general corrosion and pitting corrosion and possibly, I don't know, maybe some stress corrosion, you've got 3 defects that have to be independently assessed. But again, you can't figure out how it's going to fail if you don't have all the background information, right? So, oh, I've put in an example here. Good for me. Okay, so you have a stainless steel pipe carrying processed water to a critical circuit. What might you want to know? And this is around asking the right questions, training yourself to ask the right questions. Go ahead.
Chemical environment, so pH, temperature.
Yeah.
Concentration of your chlorine.
Yeah.
Other impurities, all that kind of stuff.
Yeah.
What's the pressure?
Yeah.
Yeah.
Yeah. Good. You might also want to ask what grade of stainless steel.
Yeah.
Right. In this room, we know there's a difference between 304 and 316, right? Like we know that they have inherently different corrosion resistance. Some people don't realize this and they're like, oh, it's stainless steel. We'll just use stainless steel, and they specify it without actually understanding the limitations of the different grades. So you might want to ask that too. But yeah, so you're looking to figure out all of these things. Yeah, so it's about asking the right questions. And we already know, right? Why are we pulling in these data? We're trying to figure out, okay, your point, you're like mentioning chlorides, right? So you're going to figure out your grade of stainless steel. You're going to figure out your chlorides. You're going to figure out the temperature. Why? FCC, right? So this is we're trying to ask what seem like very basic questions sometimes, but they're very important to ask. Then we're going to define the likelihood of it occurring. So I showed you those general probability kind of assessment tables before. These are a couple that we've used for our projects. Maybe you might have come across these already, but we're sort of using existing standards sometimes to help us to define the probability. You've got some of your C1 to C5, CX in here. We've got immersion. So sometimes using the standards can be a really good way of assigning a very justifiable sort of probability ranking to something. It doesn't always work. I mean, obviously the best is to have corrosion data from the field, but often you won't have it. So you have to sort of come up with a different way of doing it. Okay, so going back to our stainless steel pipe. Oh, did we change it? So yeah, so if you're thinking about, say we were thinking about chloride pitting in that stainless steel pipe, what would happen to the probability of that defect occurring if you had carbon steel versus stainless steel for pitting?
Depends on the pH.
Yeah. So you have to, when you make any changes to that system, you have to then reassess the risk, because the corrosion risk for pitting for carbon steel is going to be different from stainless steel, right? What happens to the probability if you add an external coating? A slight trick question.
External, meaning the outside of the pipe.
Is there only atmosphere outside, or is it
So yeah, exactly. So when you're assessing risk on that pipe, everyone immediately went to what's inside, what's the chlorides, blah, 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 what's the temperature of the foot. You've also got another corrosion circuit for that asset on the outside, right? So is it just atmospheric, or is it in a wet process in a potash facility where it's corroding like really fast, like you, right? So you have to be a little bit careful with these. Okay, and then we've got our consequence scale. I'm not sure I really need to go through this in more detail, but you're sort of assessing, next step in the process is assessing for what happens if it fails, right? So if you've got, going back to our pipe again, is the pit going to cause it be a nucleation point for cracking and the whole thing just bursts open, or are we going to end up with a leak? Right? So those have different consequences. What happens to your carbon? Now we're going to do carbon steel pipe. What happens if it's a localized form of attack versus a general sort of attack? What might happen to the consequence level?
The place would easier explode, right? Or it depends on
a lot of things, right? But generally, general corrosion is your friend, right? Because it's more easy to predict, it's more easy to measure, it's more easy to inspect and monitor. Localized corrosion isn't, right? So your consequence might be impacted by that. And what happens if it's carrying cyanide instead of water? What happens to your consequence then, right? Right. So, you know, again, we're just trying to sort of play with it and say, you have to be very careful when any changes happen. And then you carry out the risk calculation, right? Sometimes it's as simple as doing a multiplication. Some organizations use that. Other organizations, because you're doing this assessment for consequence within safety, within cost, within environment. So you've actually got different categories of risk, right? And then so what? Right? So sometimes you will see people adding them up and giving you a final risk value that includes all of those. Sometimes they'll just take the maximum, which was the sort of consequence that came out highest, right? We'll just use that. Some people say, okay, well, for us, health and safety is much more important than environment. So we're going to weight those rankings and then add them up. So there are different ways of doing it depending on the context. But you need to figure that out, and it needs to be standardized, and everyone needs to be using it. You can't have one part of the organization doing their corrosion risk assessment one way and another doing it another way, standardized. You also have to think about where's the cutoff, right? So if you remember back to my driving the car, like where's my cutoff for what risk is tolerable for this organization? And actually you'll see it varies quite a lot, right? Some organizations are like, just do the high ones, and others are like, no, medium and high, and let's make sure we're going through all of these ones as well. So it very much depends on the risk tolerance of the organization. Okay, so now you're going to do some work. You're actually going to carry out a risk assessment yourselves. So I think we've got the handouts here too. Just do it by table maybe. All right. think I can share. All right, so we're going to take about 15 minutes just to sort of let you guys figure this out. But you've to go through the case study that I've given you. I want you to have a discussion around the table using your kind of slightly different backgrounds. And I want you to come up with an assessment for the consequence and probability for the scenario and assign your risk value. And then at the end of the 15 minutes, we want to come back and I want you to tell me why you selected the risk value you did and why. What's your justification behind it? And also be very careful about noting down the assumptions that you're making in the discussion. So we are going to assess the corrosion risk for the hull structure in the bilge space of a naval vessel. We've decided already that this is a critical asset. That's why it's been included in your risk assessment. I've given you hopefully on that sheet, maybe not, but we're going to give you the probability matrix and the consequence matrix. And I want you to assess only for safety, just to keep it simple. Calculate your risk level. And I want you to think about these questions. What is the information that you need? What are the really good questions that I need to be asking? Because if you don't get that bit right, the rest of it might not go so well. I want you to define all of the major defects that you can think of that could happen for this asset. And then I just want you to consider general corrosion only for this space and just do a quick calculation on the risk assessment. And then make sure you write down any assumptions that you're making. And then also have a think about, well, how am I going to use this now? How does this help me? What am I going to do with this risk that I've assessed for? All right. So I'll give you guys, these are the probability and consequence matrices that I want you to use. And we're just going to use the very simple calculation at the bottom. I'm going to wander around. And if you've got questions that you want to ask me, you can do that as well. All right. Thank you. Thank you.
How to stop having multiple deaths. It was
Take damage and take on water.
Instagrammers, we say damage. It just gets boxed in.
Oh.
So you have to write not alive.
That's so ridiculous.
Matrix, so you can't put on Instagram. It's
Time to the body of it. Yeah, the main external structure, for the most part.
I'm really tired.
Yeah.
Oh, fine.
Part on the ship, and sometimes you want to fill it because it actually helps with like ability to.
I'm not sure if the people online can ship.
Always watch. But yeah, for a naval ship, it's different. One thing I would want to know is the ship is it like an aircraft carrier? Is it small?
I think
frigate.
So what I want to know is cathodic protection. And okay,
Say hello.
you'll love me again.
Yeah, it is.
Okay, guys, getting on.
What's your first question that you need to ask?
Like
Naval ships, they're pretty on it. They need everything. Pretty.
Talked to Zoe yesterday. That's
Okay. Maybe in the US it's a little bit better than me.
there's a lot of job opportunities in
Yeah.
Halifax and Victoria.
Thanks.
For colleagues.
Every teaching. Procedures.
studied, but then when
might materials in this environment too, because you have pumps and then you have wall structure is probably some sort of.
از چند قسمت تشکیل شده چطوری به اون That's a good question. Yeah. Keep going.
We wanted to have the drawings, right?
What would also be operating like how it's go out.
So it's, so yeah, based on the matrix there, I'd say the ship is gonna
The
be,
volume.
there's gonna be some water right there most of the time, but sometimes it'll be completely dry, sometimes it'll be higher.
Corrosion conditions, which
The top line, so yeah, corrosion exposure condition.
Excuse me, Zoe and Yolanda, can I ask a quick question? Yeah. What exactly the position of this place is in the shape? Is it a blast tank or is it like a walkway?
I was asking the same question. What is that?
So that is an absolutely perfect first question. What is it? What is it? Yeah, so you can feel free to Google it because that is a perfect first question. What is it? What the hell are you talking about? Is everyone clear on what a bilge is? So well done, Marshall.
Thank you.
We're kind of not sure if it's the right question. We thought maybe it's just we are lacking of knowledge.
There are no stupid.
There are no stupid questions, right? It would be worse to continue not knowing what it is, right? So ask the question. You like feel free to use your phones, like look it up. See if you can find a visual on it. So well done, Marshall. Thank you.
But this is all also gonna collect your sand, debris, or everything. And you can't clean it out.
Other things, say, for naval ships, that means, but that doesn't really give us the knowledge of where.
The shape and the water.
Yeah, well, yeah.
Design.
No, I mean, like, it's gonna be in the sea, it's a naval ship.
Yeah.
You're not gonna put a naval ship in a lake. Oh,
That sounds like an assumption to me.
it is, for most strategic assets, naval based, they will be in a lake periodically, but they're not gonna be.
They could also be in brackish water, but they could also be in the lake. They also go in fresh water for Canada. So
Yeah.
that's a really good assumption to make that you're saying, right, this vessel is only going to be in seawater. That's our assumption.
Yeah.
So that's good. Excellent.
No بدنی اصلی.
Fraction too.
And of course, structural design.
That's for sure.
Like,
Depends on the value, could be well sorry.
That's why like the size of the ship also. There are rates. Yes, yeah, because your engine room is probably somewhere right there.
risk assessment اونو بر اساس جنرال.
میتونه فرتینگ باشه میتونه ایک میتونه استرس باشه
What happens if
مثل سایه هیچ بهش سایش
دیوشن فوژنه.
چی؟ فرتینگ اگه که ذراتی
Try.
this is stagnant?
مثلا سندی توی فلویدیت باشه اون میشه ایروژن کروژن، اون نمیشه فرتینگ.
Erosion.
فرتینگ دو تا سالید بر هست.
Mechanical line, even if you have plasma coating, you will always have like sand going in. You always lose it after some time. So the
ایروژن
critical
کروژن.
component, I would say, is the pump.
Sand.
Yeah, well, sand, I mean, like a general granular structure within the body itself. Sand. No, but it's just like a sense like the boot is like it will kind of then whatever will be exposed, so it will go against putting whatever. So even if you like
اگر پینتینگ
Sure.
داشته باشه بعد پینتینگش آف بشه اون
like
زیرش
putting down to that.
می‌ره.
So this is just like an open space, right? Like it's just the fact of the bottom of your ship. A lot of the time, it's like a confined space. Sort of. Feel free to disagree with me. it really goes down there because your deck is here, and then you would have to like send people there to clean it, so it's a dark space, very hard to like, inspect and everything.
Oh, yeah.
I don't know where exactly your fault would be, but there'd be some sort of
So I switch check.
hose that takes it to your.
She,
But I call it Davis.
is Jordan still alive?
I don't know. I didn't.
Means it's gonna look for debris. Unless you have some sort of filter on it, obviously, but even that filter.
So filter maintenance.
Yeah.
I think I'm talking too much. I don't think we've already run out of time this morning.
Stress will also be important because
I
it's a very sharp flow that it holds itself. But
you know, in that movies you were showing,
Safety concept.
they were talking about the
It can be a 5.
Turn my office.
Your bill is just working.
They were talking about like warning symbols that distract people from like they're always cleaning.
Yeah.
I think also in Chernobyl they had that problem.
I
Yeah.
think it's
I was thinking fucking
I'm like,
the speed, gas.
yeah, I just need like no blinkies. I'm focusing in on these 3 risks and that's it. Really?
So you actually separate it, so okay, one area, one pump doesn't work, still have.
Oh, it's so because it is really distracting when all the things come. You're actually driving.
I don't even take how many pumps.
Atmosphere, how much is safe? Oh, I was there.
I talk to everyone when I'm in the car. That's what my kids.
Has immersion style.
It's pretty sure that's that maybe plays into class of ship, size of ship.
Now when the programmer's one, right?
You didn't know I was. Yes, for sure. Driving. No, it's not how it works.
Very commensurate activities.
There's element of cohesion any functions. The wall shit. Okay. Outside.
Another one I was thinking for this risk calculation matrix, you were talking about what is the acid and stuff. So Shiva, the person that spoke about the electrolyzers earlier, when I was doing the interviews, one of the big, yeah, she's the CRC in Columbia, renewable energy.
This is the
But
the risk.
I am for
Training, so that's the
project
probability.
level which is safe.
Probability of failure, the complete non-failure. Probability low.
squeeze our
Probability that should be corrosion is pretty high.
And
Even that is
from their whole city on diesel generating it
based
right,
off of just
super expensive.
right, we're not doing
And
So, but not just, so general corrosion isn't gonna necessarily lead to failure, except if you start to eat through your pipe wall or your steel wall.
They know
You have general corrosion or you have sediment. Crevice, like,
So it's another assumption.
it's like $1 a liter having a stand that goes
Really said that plays a big effect in the water calculation.
So your solution then
It's
has
also
to involve
you're probably not doing stainless steel because it's too expensive, so you're likely doing carbon steel.
probably carbon steel and trading provided exposure.
well, and like slowly reducing your reliance on
Exactly. So
there's this really
C5B, just exterior atmosphere.
okay.
So we're doing.
Over there, yeah.
So it's
like, and usually in those communities,
pretty periodically, so you have like differing levels, so you.
Total cell
Zero change management.
Cycling.
Aspect. It's more the fact
It's
that
like us going in.
do risk assessment.
help
When we
sailor.
do the risk assessment, we'll have to do a bunch of assumption about what is and so
It would be important.
in the still sometimes.
But we don't know. You like stay.
Yeah. Like what is nice.
Yeah, it depends on the age of the ship for sure,
How was it? How can we improve it?
maintenance cycles.
And what is mild?
The
what
critical
we used to
component would
do.
be the pumps.
My Navy client refuses to work.
Then
They'll like
you could then think about through wall.
just come in and they know everything.
Because this has direct, like you'll definitely have some sort of standoff.
well, that they
They're
were thinking about
reinforced from
hiring
the outside too for like
yeah,
damage to contact.
do the deployment of all the, or like come up with the.
This is pretty, probably not.
Seattle has like
But, you know,
ships, and so they do
maintain it. Your pump is your critical
infrastructure that
If this does fail, it's very high.
the existing ships. It's kind of
In why it's better than Deloitte.
I would say.
who doesn't Andrew work for? Yes.
So the age of the pump is like so slow.
Yeah.
We didn't know.
We don't have the right fish.
Don't know. I think we'll give everybody a couple more minutes and then we'll come back together.
I was captaining a ship and my build pump to fail. That one fish areas of
Nap time.
Just been
Yeah, reaching your hole, you won't be thinking, so. You can say nothing.
What's the pattern she had? Wait, you know, the dishwasher, so she's mowing the grass.
Once you find like the is a big gift.
No, it's probably have like
Your ship sink. Yeah.
train all your people.
It's the warning.
Okay, can every group assign a spokesperson?
True, Irene, because if you've already.
We always talk.
We always talk.
You're the one that knows fact. You're the boat captain.
No, I already wrote.
I went down with the ship.
I wrote you as captain.
I went down with the ship.
Your ship is still sailing.
All right, teams, let's bring everybody back. So has everybody got a spokesperson? Middle team, you look a little bit more ready than everybody else, so we'll let you guys go first. How did you get on? What was your risk assessment? What did you come up with?
I think just in terms of like going through the list of things, so what information did we need?
Yep.
There's a lot, obviously, because we don't really know much.
Excellent. Good.
So, main thing is like what materials, what is the ship like in terms of dimension, age, and like class, stuff like that. What type of inspections are they doing on the day to day?
Yep.
Are there welds present in the area?
Yep.
Let's see here. What the biosystem is like. That's something that Yolanda brought up as well,
Yeah.
because it is a stagnant pool at the bottom of your ship. So
That's an assumption.
that's assumptions.
Yeah.
about later.
Yeah, good.
One of the assumptions, yeah. So I guess
Good.
I guess down the list, like what assumptions? So Brock brought up the point that we'll assume that it's in the ocean. So you're in a highly chlorinated environment, lots of salt.
Yep.
So that, also that there's multiple pumps, not just one. Again, that ties back into what type of class of ship it is. And then also we eventually started talking about like, because you also gave us the table of like what materials we should use. So again, because we're assuming that this is a stagnant and it's constantly submerged and levels are changing, we put this at around a probability of around 4 on that curve.
Right. Yep. Good.
And that leads into the material selection of like what material we would use. We would think, and again, this is another assumption, that you wouldn't use stainless steel for cost and also the effect of pitting corrosion.
Yep.
Not good. So we assumed carbon steels. Carbon steels are material.
Yep.
And so then again, it's also what type of coatings are involved, what type of maintenance to that specific material.
which cathodic protection they
And
use
cathodic-
and how they maintain it.
Yes, right.
Yeah.
So that's a lot of things to go into there. So that's kind of a lot of the information that we needed.
Yeah.
And then going into the safety consequence of what happens if that does fail, obviously. So
From general corrosion.
Yeah.
Okay. What did you end up as your risk value at the end?
we ended up with risk value of 16. So we put it at a critical consequence and then also probability of around 4.
And more because it's like you kind of lose the asset at that point. It's very hard to recover the asset if you get general corrosion through the hull. And then think of if you're in an operational environment too, where you need to use that bilge pump because maybe you took on damage or it's raining or you're in a storm or something like that. You have to be able to handle that.
Yeah.
Yeah. So that's where
One question we would ask is how many backup pumps or how many points of failure they have. Because
Right.
if one of the pumps is failing and the ship is sinking, then the consequence is bigger than if you have several backups.
So what if I told you that originally the design for this ship, the bilges were supposed to be dry? They don't operate them dry, but that means that there's not that redundancy built in for the pumps, right? So it's like that's the piece I'm saying, like where you need that operational information to inform your risk assessment, right? So I think you did a good job there with your questions. Good. Let's see this group. Who's your spokesperson? Yeah, go ahead.
Yeah, we didn't manage to do everything, but then
Okay. Yeah, absolutely.
on the information that we thought may be important to know, the range of the temperatures of the water in which our ship will be operating on, and the kind of material the house structure is made of. Is it stainless steel? Is it carbon? We just searched on the internet and they were saying it's usually made of mild steel. We didn't verify it though, but then we also need to know like the volume of the components, like this ship, what is it going to be carrying? As in, we need to know the general mass, the speed, so that we are able to know that is there going to be maybe any erosion from sands that lead to maybe stress cracking, which is going to be a little minor. And we thought maybe we might also experience thinning of the material resulting from that erosion from the sand. Then on the risk assessment, on the probability matrix, we came up with 3.
3, yeah.
Yeah, we hadn't discussed any explanation for that, but then
gut feel was a 3. That's not a terrible place to start, right? Because it makes you sort of question it, right, with your team.
Yeah.
Okay, and on the safety consequence, we said it can be critical. Let's say if this is ignored for a long time, maybe the erosion and the likes that might lead to maybe leaks. And if it's ignored, it might lead to maybe not really sinking, but then water might start to get into the ship, which might be cause some detrimental effects. Then we also
good.
So our
but you didn't come up with a calculation yet, or you did?
Okay. To 12 because yeah, we had a 3/4.
Yeah.
Yeah.
Good. Okay, so already you're starting to see that there's some differences, right? And so this is where having that broad range of experience in the room can really support you to kind of really discuss, is it a 3, is it a 4? What are the assumptions that I'm making? Okay, good. And what about the team over here?
So the question that we had in the beginning was actually what is it?
Yeah.
And then we found out it's at the bottom of this ship.
Yep.
And then what we need is what's the material, what's the structural design of that one, and is it coated or not, and what's the environment like? Is it completely immersed in the water?
Yep.
Then based on that one, the second question for us was like if it's moving in the sea or in any environmental any water like body of water, it would be erosion because of all the bubbles that is going on, or the sands that is in the sea. And then, of course, it should be some biofouling and leak going on that part.
I thought you might pick that one up. That's good. Yeah. Yeah.
If there's any coating and there's any coating failure on that one, there should be some crevice corrosion going on because of the pits that everything that is provided for that one. And also, if there's any bolts or joints in that, and there's differences between the material, there should be galvanized corrosion. So because of the design that we were assuming about immersion, we got that one as at immersion level of 3. And then thinking, we again Google it, what's the main material that it is used, and it's a mild steel, AH36. Usually it was set in the range, which is carbon steel, and it would again be IM like 4, and the probability would be 3. And we were thinking it would be critical if we think about the failure, general corrosion failure of it. It would be like sinking of the ship or anything like that. So it would be highly critical. Then our risk calculation would be around 12.
Okay, excellent.
Marshall wants to say something as well. Online?
Oh, go ahead, Marshall.
Yeah, let me unmute myself and first I googled what that English word means, and then I found out it's outside of the blast tank. Because the first thing I was thinking about, the bottom of the ship was outside, but this is inside, so we're not talking about anti-fouling, right?
Yeah.
And as far as I can remember, the material should be carbon steel, 8mm thickness, usually, right? Welded together, because when they were built, they were welded, built in sections. And the coating system should be, I guess, this is an assumption, it's 60 microns, 2 coats. So altogether, there may be 120 microns epoxy. And also it's inside, so UV degradation shouldn't be a problem. But over time, there is mechanical damage, and also every coating is defective. There is coating delamination. And but the water shouldn't be salt water because those are inside the blast tank, but this is inside the ship. So it's generally clean water with some dirt, oil.
I'm going to stop you there, Marshall.
Yeah.
So just to correct that assumption, so that there should have been some more questions, I think, in the room around this generally. I think people are making some assumptions about what's in the bilge, right? It can be seawater. Your ship could be sailing through fresh water. It could be sailing through brackish water. They also use it as a dumping ground for other chemicals on board.
Whoa.
So there could be any kinds of things in there, and the composition varies over time. The immersion level varies over time.
Great, thank you.
So that was an important question, I think. I think this table in the middle kind of had that question around what's it sailing through. So you almost got there, but there was another question on top of that. Is that all that's ending up in the bilge? Right?
You made that.
You made that decision. Yeah. Yeah.
It is the bottom of the ship. And if you ever on a ship or around a ship, it's always wet.
Oh, it's always, yeah. Yeah. But there are other things going in it, not just salt water. It could be oil. It could be other reagents. Yeah, go ahead, Phil.
I was just gonna having cleaned many bilges in my life.
This is our sailor in the room. Yeah.
Honestly, the lowest part, all the crap that is leaking or whatever goes there.
Yeah.
You have it tells you also when the propellers go through, they're supposed to leak into the bilge.
Yeah.
And watch them drip. That's how they get lubricated. So it's kind of important. Your inspection tool is also the bilge. So it tells you if you want to know if the boat is seaworthy, you literally go to the bilge and see how fast the water's coming. Right. So it's really important to have it available, right? And your inspection or your safety consequence matrix, how does being able to see something rank there?
Normally we deal with inspectability as part of probability, right? Because if it's something that's occluded or difficult to monitor or difficult to measure, the probability of it happening, we just assume goes up because can't see it, right? So you play around. It's not so much with the consequence ranking, but it's the probability ranking. Yeah. Okay, so I've actually got some slides on this exercise, and then we'll stop for a break. How good were your questions? I hope that this exercise has shown you that the level of questioning that you need to do to start these risk assessments is large. You need a lot of different people in that room. You need a lot of different sources of information. It's always a very good question to start off with. What is it? Right? If you don't know what it is, you don't know, you can't go any further, right? What is it? What is in the bilge space? What's it made of? Is it coated or protected in some way? We had are there biocides? Are there coatings? Are there cathodic protection systems in there? What's the current condition of it? What are the likely failure modes? Like you're sort of trying to figure out, like it's a bit like a CSI. You're like a forensic person, right? You're trying to ask all of these questions to figure out the most likely scenarios. So with any corrosion engineering, anything, the quality of your questions will determine the quality of your solution that you come up with. So really, really important that everyone starts to really think about at the beginning of any project, am I right? Am I asking the right questions? Right? So if you'd asked your person in the room that knew what a bilge space was and has been working in these bilge spaces for years, me, I was like, I'm here as a resource, but nobody actually asked me a question, right? And I could have said, well, I can tell you what bilge space is. I can tell you what's in it. You know, I think everyone figured out how important it was because obviously we need the water on the outside of the ship. Material of construction, right? You could have asked me that question. What's the coating protection that they've got in there? Actually, they've got coatings and they've got sacrificial anodes in there, right? So what's the data? How has it been operated? What was meant to be designed dry, which means that at all times they were supposed to be pumping it through the water treatment and getting rid of it, but they don't do that. The operational behavior is different to what we expected. Yes, go ahead.
Is that also just like a design decision to make it cheaper?
Don't know. Don't know the answer to that. Yeah.
One of the interesting things you were saying there's a coating and a sacrificial anode, but one of the big issues that's coming up in the sailing clubs these days,
yep,
is the electrical systems on the old sailboats are not grounded properly. So you and also all the plugs that are
straight. Yeah. That's more of an issue, I'd think, for impressed current systems. We do have that issue with the naval vessels as well, but these are galvanic, so they're easier.
Yeah, just everyone's propeller is broken at the end of the year.
Proper grounding.
Welding.
Yeah.
Because they need the grounding, and if
there's
stray currents and problems.
Then it gets complex. Yeah. So use your team is the learning from this. You didn't use your team, right? So you need to pull in the expertise, and it's 1,000,000% better to say I don't know than to go ahead with assumptions that you don't have the background information on. We came up with some good assessment on the types of defects that might be present. Some information on our assumptions around exposure. You know, obviously the hull, there's going to be, I think somebody, maybe this middle group again, that you came up with it, you know, there are going to be stresses involved because it's a structural component. So there are stresses involved. Right. So I think you were good about putting down the assumptions that you made, but because your questions weren't always the right questions, you made some assumptions where you should have been asking questions. So just to watch that, right? We've got a bit of agreement in the room that there's a risk level of 12 and then a 15 in the middle. But this is really supposed to be the first time you kind of go through a risk assessment like this. you'll come up with your numbers. And then the intent is to use that as a discussion point with the experts in the room so that you can agree and justify the selection that you've made. And that's where you start to really get the input from all the different people. Okay, well, no one answered this question yet. How do you want to use this information now? You guys have got 12 and you've got a 15 risk rating. What's the next step?
Would come to the mitigation
Yeah.
strategy that we want, or monitoring strategy that we want to consider.
Yeah. So if you end up and everyone's in agreement that it's a 12 in these groups and you've had your discussions, and we'll ignore all the assumptions, everything at the moment, but you've decided it's 12, you might be doing something a little bit different from these folks in the middle who've decided this is a much higher risk, right? We're going to be going in and we're going to get, the hull surveyors in on a more frequent basis because we know X, Y, and Z, and we think the risk is. So you're using the data, so this is why your risk value has to be really well justified and really well understood, and you've pulled in all of that experience so that you can make good decisions on what's the next step. There's no point doing these and then leaving them in a spreadsheet, right? You've got to actually use them to push actions, to implement actions. So yeah, so the first thing I like about these risk assessments is that you know what the risk is. It's visible now. You have now got a tool to start communicating that risk with everybody else. Leadership comes up to you and says, you've requested this budget. Why? You're able to say, well, following the organizational risk tolerance profile, we have assessed this in a structured way, and this is the value that we're getting, and these are our high impact actions that you don't want on your books because they're above tolerance. That's a very different conversation to saying, well, I'm a corrosion engineer and I think you should do this and it would be good. You're talking to a different audience, you've got a tool, right? You can also use this to design tests to gather more field data. Can you validate your assumptions? Do you have enough data behind your assumptions that you've made? Maybe not, right? Often we're doing these risk assessments with data gaps. What controls are we going to put in place? Yes, maybe we should put some biocides in there. That would be a good idea, right? Should you be inspecting more? Should you be using different inspection techniques? Is the NDT technique that you're using appropriate? Right? So using UT spot checks, ultrasonic thickness measurement spot checks for a pitting corrosion is not going to give you the answer. You're not going to be able to pick it up, right? How do we prioritize resources? Interestingly, this one's come up quite a lot around due diligence reporting, right? So if you have a catastrophic collapse, the first thing that people are going to say is, have you been managing your, I don't know your tailing down properly? Where's your documentation? Where's your structured process, right? So there's a due diligence perspective as well. And also, are there design improvement opportunities? Is the coating that we've got on there right now, is it working well, right? We've just started to change out the coating and the bilge spaces for the Navy because it's not functioning as we expected it to, right? Lots of other things too. Yeah, go ahead.
Here, like, since we're talking about a Navy ship, so
right,
more than just ship floating, because the hull is probably also acting as some kind of armor in case it gets shot at, which like it's not in the risk mitigation. So like, are they also testing the ships, like not just their watertight, but they like blow stuff up on it to make sure that
Are we blowing up the few ships that we currently have? No, we're not doing that. No, I leave that to the structural engineers, so that like it does come into the design of the ships. But I don't know anything about it.
Be a fun experiment.
That would be a good question to ask. Yeah. So, not to frighten you, I know we just did a very simple example, but here's one I made earlier, right? These things get quite complicated and there's quite a lot of information in them. I don't know if I can actually show you it, but maybe you can kind of see anyway. But there's just lots of steps right? You're having to think about a lot of different things, and this is where you know, making sure you've got the data to answer the questions comes in, right? So you always do a risk assessment, and you're doing you're figuring out all the defects. So one line by line, there's a defect. You assess every defect. You're coming up with an initial risk ranking, and you're putting controls in place. So these things can get very very complicated. So we just did one for a Navy frigate vessel, and we had 16,000 line items, which we then decided we should probably not have this in Excel. So now we have an app for it. But yeah, it's so they can be complicated, or they can be simple depending on the sort of the way that you structure the program, right? So let everybody have a little break now. Yeah. So we're going to come back. What time?
26.
10 for 6. Well, I've got us starting at 11, so you can only have 15 minutes because I spoke too much. Sorry. So we'll come back. We'll come back at 11.
I remember.